It's 20 minutes more. 20 minutes is gold these days. 20 minutes more to play with the momentum and position stuff. Let's see. Um, momentum, and position um, relationship, quantum mechanics. Yeah, certainly, the principle is one thing. This is what's been. So I know people keep talking about the Fourier transform. But that's kind of the point. The position representation. In the position representation, position is the operator of multiplication by x, whereas momentum is a multiple of differentiation with respect to x. I think that makes sense, right? These observables are not Fourier transforms of each other. In the momentum representation, momentum is the operator of multiplication by p, whereas the position is a multiple of differentiation with respect to p. Okay, give me a second. For 20 minutes might turn into 5 very soon. But that's good. Okay. The reason why these representations are prepped for position and momentum is the fact that in both representations, the commutator is satisfied the canonical condition, the quantum analog of Poisson bracket. The Fourier transform comes in only as the means to switch from the position representation to the momentum representation, or conversely. The reason is that apart from a factor, differentiation of the Fourier transform of a function is equivalent to multiplication. Differentiation of the Fourier transform, so it's just used as a tool. The differentiation of the Fourier transform of a function is the equivalent to multiplication of psi and differentiation of psi quantity that is conserved as a consequence of transition symmetry. Translation operator. This is too much. I don't know what the generator is. The probability density of the momentum is the Fourier transform of the probability density of the position. So because here that was my point in here is that why you're multiplying? This is the problem I have. Conversely, dimensional wave function of momentum space can be expressed as the weighted sum of orthogonal basis functions. I'm not so sure why you're just multiplying here. Turns out to be the inverse Fourier transform. Momentum space. It's the sum of its items. Okay. This is what's hard. Transform a position wave function to momentum wave function. There's a similar problem that the one I'm trying to approach. Constant when starting with par B. Normally you would change the limits of integration and double integral, but that's not applied. The momentum space wave function is obtained as the Fourier transform of the position space wave function. Okay, but why? That's what's not intuitive to me. How to get the position operator in the position representation. That's not what I'm asking. The position operator is given by these as these eigenfunctions. Okay, so essentially, okay, so these are eigenfunctions. And then you're saying that and eigenvalues are. So similar decomposition of the wave function in momentum space, right, can be made in terms of the eigenfunctions of this operator. It's the position operator. The position operator times. So look what we're doing here. So you're just doing the position operator. The position operator times differentiation of the Fourier transform multiplication of the Fourier transform. Self-define momentum as the quantity is conserved as a consequence of translational symmetry. It's too complicated. Time frequency, space momentum. Momentum is defined by how a solution of the wave equation evolves dynamically. So given the Fourier transform is not general, but limited to certain evolution laws. See, that's also why I'm looking into understanding that a bit more fundamentally, because I'm not so sure that applies to all these situations. You know, like if I have oh, okay, I mean, wait a second. So that starts to make a bit more sense, as in like why is it an integral, right? Because it's in a way the sum, right? You're integrating over 3D space in this case. These psi r is, you have to think of psi r as the way, so psi is the wave function in position space. That would be in the normal situation is just like an integer, let's say, right? Like it's or a real, it's like the position, right? Um, Times, and then there's this shit here, which is basically, I don't understand why this has to be uh, the eigenfunction though, and why times? Hmm. Can be expressed as a weighted sum of orthogonal basis functions. Okay, but these are, so this is where, okay, so this is where, okay, so you actually introduce that. Okay, give me a second. So you're introducing here it's basically you're saying you're saying, so you're saying the position operator is basically the derivative of the momentum operator. That's how you're introducing that other thing. So that you're doing that relationship. And then you're saying you can express a wave function for y equal. So you can express a wave function in is it easy to work from position space? This is how to transform. This is how to get. Suppose we have a three-dimensional wave function in position space. Then we can write this function as a weighted sum of orthogonal basis functions. That's fine. That's fine. I don't know why we're doing this like that in the continuous case. Why are we adding k space in here? It is clear that if we specify the set of functions psi sub k, say as the set of eigenfunctions of the momentum operator, the function psi k holds all the information necessary to reconstruct psi r. So here it's saying as the basis Now we're using the momentum basis. Oh God, that's actually more complicated than I thought. It seems to be, and I think I actually have to finish up. Babies arrive. So, it's just is it just a change of basis? How do you change basis? So how do you maybe that's something I could take a look. Is like how do you do quantum uh, basis change continuous? Is there what's the recipe for this change of basis? Continuous basis. Change of basis. Essentially, that's what it is. You're changing the base. Um, you're expressing it as in the that's actually quite tricky, and that definitely how do we understand continuous basis? That's probably one thing because discrete bases are like easy, right? Think of like you think about like you think about like X, Y, Z, right, as being like the 3D bases. But in this case, we're saying we're using position as a basis versus using momentum as a basis. And what does this mean at all? Like, I didn't even. I mean, I think I came across that concept before, but I have no idea how to read that. Like, how do you understand continuous basis? That's probably a good thing to do. Change of basis. How to can change continuous basis? Because that might give me a more generic, not continuous change of basis, but uh, continuous variable. I don't know if that's the right change of basis. Let's try to do that, which seems to be a bit more basic. Change of basis, because that is definitely, change of basis. But how does this translate to? How do you do that for um, continuous basis? That's kind of the form. I think that is probably even the more generic basis than just going with the Fourier transform stuff. That's pretty nuts that the eigenvalues are actually all the reals. Hmm. Okay, I need to understand that. Yeah, this relationship. What does this mean though? The projection? I have to refresh these as well. Yeah, yeah. Just find. Why is it also so zoomed in actually? Oh, maybe because of the streaming. Okay, let me read that calmly and come back to these. That might help me a little bit. Try to understand continuous basis a bit better. What does this mean at all? And whether that enlightens me a little bit more. Cool. See you next time. Oh, great. I managed to get 20 minutes in.